name is Bojan Brodic, and I'm a postdoctoral researcher in geophysics at Uppsala University in Sweden. In this lecture, I'm going to talk about a part of my research interest in near-surface seismic imaging and discuss a case study analyzing the feasibility of 3D random seismic arrays for urban site characterization. This study was conducted together with Alireza from Uppsala University, Mats from Firenze, and Johan from Swedish Transport Administration Agency, Trafikverket. This lecture can be essentially subdivided into 4 different parts. And in the first part, I will introduce the motivation behind the survey, briefly describe the site, go over some data acquisition and data handling strategies. Following this, 2D bedrock seismic imaging using a seismic landstreamer will be discussed. Next part of the lecture analyzes the feasibility of a randomly distributed array of seismic receivers for active source seismic imaging. Then following this, an analysis and an overview of the ambient noise field recorded on the wireless receivers at the sites during approximately 7 days of the survey will also be shown. And in the end, a general summary and some conclusions will be drawn. Which brings us to the first part of my lecture. The survey's area is located in Varberg city in southwestern Sweden, where a 2-track high-speed underground railroad and a train station are planned to be excavated. Along the 2 locations of the planned tunnel track, soil samples taken prior to the excavation process have shown high concentrations of various contaminants such as chlorinated hydrocarbons, different kind of chemicals, metals, etc. The contaminants are related to the historical works of the chemical cleaning and precision mechanics industry operating at the site during the 20th century. So our overall goal at this site were to image the bedrock morphology and zones of weaknesses that may or have potentially been already used for contaminant mobilization and locate potential contaminant migration pathways. We can see now on the figure shown here with green, our planned tunnel track shown, and the white arrow showing our site at NN13. The highest concentration of the contaminants, if we look deeper inside the map, is located along the 2 zones, Zone A and Zone B. Zone A appears to be connected to the origin of the contaminants and follows a known bedrock dip, while Zone B is relatively further away from the origin, which brings questions such as, are the Zone A and B connected, and do they come from the same source? Also, during the excavation process, the contaminants may mobilize, which brings the question, where and how will they move? To acquire the data, we used a combination of seismic landstreamer and 134 wireless seismic nodes. A landstreamer can be thought of as an array of receivers that can be towed along the ground and record seismic data without the need of planting the receivers firmly to the ground. What makes Uppsala University's landstreamer unique compared to other landstreamers available is that it was built using 3-component digital-based MEMS sensors. The digital nature of MEMS sensors, together with digital data transmission, makes the entire system insensitive to electric or electromagnetic noise pickup. Tilt angles of all 3 components are measured, all signals are located along a single cable, and the entire system is GPS time-tagged, enabling linking it with wireless nodes for passive acquisition or to cover inaccessible areas. The photo shown shows the entire landstreamer assembly with its orange-bluish shapes mounted on sleds and connected with the non-stretchable yellow straps. The spread itself at the site involved 3 elements. First, we deployed 45 wireless nodes along existing train tracks. Following this, 89 wireless nodes were randomly distributed along an area 350 by 300 meters. And the last element of the spread were 12 active source landstreamer seismic profiles. At that time, the landstreamer was 240 meters long with 100 MEMS sensors. And as the source, we used a 45 kilo accelerated wave drop. The wireless units on the train tracks were used as an extension of the active source seismic profiles. Aside from the main goal to image the bedrock using 12 active source 2D landstreamer seismic profiles, we thought of adding an extra goal and evaluate the feasibility of 3D bedrock imaging using active shots and the wireless nodes, and also analyze the ambient noise field properties in terms of size of array response and retrieve passive seismic data using the cross-correlation method. Which brings me to the second part of my talk, dealing with the analysis of 2D seismic data acquired using the seismic landstreamer. The bulk of this talk, or the bulk of the 2D talk at all, was done by my colleague Alireza Malikmir from Uppsala University, and the details can be found in the reference shown. I will just here briefly show some field photos, and need to mention that the survey itself was very challenging. So we can see some field photos where the landstreamer was deployed along the pavements. We can see also the wireless units used as an extension. We can see a train coming into the station with wireless units located over there. And also there was some garden geophysics involved with the landstreamer being deployed in people's gardens. This is an example of one of the more difficult seismic lines, and this is where the versatility of the seismic landstreamer comes into play, where we can see the seismic landstreamer coming out from a hole in the wall and extending the line from the other side. And this is the beginning of this line, where the landstreamer is located and goes through a warehouse. The 2D seismic data was treated in a more or less standard way for these approaches. So it was used for 2D first level tomography. It was about 75,000 traces, and the tomography was done in 3D space using PS Tomo code. Average RMS errors of the result obtained was approximately 2.5 milliseconds, and we can see with black bars boreholes that were existing on the site prior to our survey, and the red bars showing the boreholes that were done after our survey, where almost all of them stroke weakness zones in the bedrock. We can see this example from profile 27, and now we can look at another example from profile 33, where the red newly drilled boreholes are intersecting the weakness zones. These weakness zones were previously unknown. The top figure shows an aerial photo projected onto an elevation model with the survey elements marked, while the bottom figure shows a 3D overview of the P-wave first arrival tomography results obtained from the 2D landstreamer seismics. The black lines show drill depth to bedrock, and we can see that the bedrock depth matches relatively well with the boreholes shown. However, we can see that this model shows a lot of gaps. What is also worth noting is that there is this zone where the high velocities come almost to the surface, and this is a known bedrock outcrop. So next step was to apply the BIM concept for automatic bedrock depth detection. I'm not going to talk too much about BIM here, and if you're interested in it, there is an e-lecture by Matt Svensson on EAGE's lecture series YouTube channel discussing it more in depth. Essentially, in the first phase, it is a 3-step process that compares the bedrock depth versus the tomography velocity and obtains a velocity surface judging from the intersection with the boreholes. So the figure shown to the left shows the result of the first stage of the application of the BIM process, and we can see our A and B zones that have highest concentration of contaminants. However, there are no obvious lineaments connecting it to the origin of the contaminants in our site 10 and 13. However, if we now apply a second stage BIM workflow, as shown there, which is essentially subtract our bedrock surface that we have obtained in the first step versus low velocity zones that we obtained from the second BIM stage workflow, we come into our second result, which shows obvious lineaments, and we can again see our 2 zones A and B, and we can see this lineament that clearly connects zone B to the origin of the contaminants and our site Renan 13. So to summarize, from this output, 4 major lineaments were found. The northeast-southwest one was previously unknown, and what is also possible is a network of fracture systems, and this should be considered prior to the remediation process. So we obtained a good velocity model and a good bedrock and bedrock weakness zones model that has been tested and validated using the new drilling campaigns. However, could have we done the survey differently and obtained similar results without conventional 2D seismic method? With this in mind, we exclude all the data recorded on the landstreamer and focus our analysis on the GPS time tag source locations activated along the landstreamer and recorded only on all wireless seismic nodes at the site. Essentially, the question here is if we could resolve the bedrock morphology, if we deploy our wireless nodes in a random manner, take our seismic source, drive it around, activate along the streets or pedestrian pathways wherever possible, and obtain a similar seismic image. Before answering this question, we can again look at some field photos. And the details of this work can be found in the reference shown here. What deserves to be mentioned in the first place is that the wireless nodes were deployed in really difficult areas such as school backyards, residential gardens, side of the roads, very busy streets, and sometimes we had to hide them behind bushes, etc. And we can see the arrow here showing at 2 of the wireless nodes in the bushes just next to the road where the people are walking. Again, in the busiest streets, we had to do the data acquisition during night hours to avoid interfering with the traffic. And we can see here a photo where the wireless nodes were deployed along the parking lot and our seismic source used again. So wireless data handling was based on downloading the 3-second segments, starting from the GPS time-stamped signatures of every source hit. Then we sorted this data, picked the P-wave first arrivals, and used the PICs for 3D travel time tomography. Here, we can see an example of the shot gatherer, and it is a very noisy data, and we can see the red dots showing our PICs. So compared to the active data that had about 75,000 traces and 75,000 PICs, here, number of PICs was about 23,000, and all of them were used for P-wave first arrival tomography and in PS-TOMO code. This figure here shows a relatively uniform subsurface illumination from all the sides of our random array. And the lower figures show that our picked first arrivals and also residuals after the inversion align along a thread. And the final RMS obtained of our velocity model was approximately 3 milliseconds, with the cell sizes for the tomography used 4 times 4 times 2 meters. So top figure again shows our aerial photo projected on elevation model with the survey elements marked together with our A and B zones. And what needs to be noted this time is that the red dots represent only source locations, not the landstreamer locations. The bottom figure shows our velocity model obtained from the 3D travel time tomography. The black bars shown here are boreholes, and judging from the intersection with the velocity model, we can take out one surface that would represent an average borehole depth velocity across the entire velocity model. So if we now take this velocity, which was in this case 2,500 meters per second, and this velocity is shown on the top of the figure, and if we color code that velocity, we get our depth to bedrock, where 2 preferential directions show up, and these 2 preferential directions correspond very well with our A and B zones. And again, we can see that B zone appears to be originating from the same Renan 13 site and has the same source of contaminants. If we now compare the 2 independent results together, we can see on the left the 2D seismic model obtained using the BIM approach versus our 3D random array model. Both models resolve the same 2 directions, concluding that Renan 13 is the source for both A and B zones. Which brings us to the last part of my E-lecture, where I will try to analyze some ambient noise data downloaded from the random array wireless nodes. So approximately 7 days of ambient noise has been downloaded from the wireless units, and it was downloaded in 30-second long segments with 1 millisecond sample rate. If we look at the figure shown, we can see an azimuthal array response that has 2 preferential directions. These 2 directions correspond well to the train tracks crossing the site and the main streets crossing the site. The black triangle in the center represents the center of our array. To obtain an overview of the ambient noise characteristics, the data has been segmented into 6-hour segments, and I'm showing here the morning rush hour from 4 a.m. until 10 a.m. We can see here a power spectral density plot calculated within 3 minutes windows. So the numbers showing up here on the screen are timetables of only one train coming into the Varberg train station from a nearby town. I took only this train because I wanted to avoid confusion with too many numbers. And we can see a clear signature of 522 train coming into Varberg station, then 552, etc. If we look at the signature of this 522 train that live in the seismic data. We can see the shot gathers shown here. And now we can focus on the amplitude spectra produced by this train and a noise window just coming before it. We can now focus a bit more on the ambient noise and examine how the amplitudes across our array change with time. Here we can examine a signature of one of the trains just passing through Varberg Central Station around 4:30 a.m. Note that this train does not stop, it just passes. And this train is indicated by the red arrow on the power spectral density plot. What we have calculated here is the RMS amplitudes within half a second time windows, and we can monitor how the amplitudes change across our array. So we can see slowly in the southern part that the car is passing through the street, and then in the southwestern part, our train is coming in, going over our receivers slowly, continuing, and exiting along the train tracks. If we now focus more a bit on our power spectral density plots, we can see that numerous monochromatic frequencies can be noted, and some of them are indicated by the red arrows. So going back now to our train amplitude spectra, we can also see these monochromatic frequencies as sharp spikes. And what can also be noted is that most of the energy that is induced by the trains is in the low frequency part. So with this in mind, we downsample our data down to 5 milliseconds and start the process of retrieving passive noise data by removing this electric EM noise contamination of the monochromatic frequencies. Essentially, this is a more or less standard approach that is used for ambient noise analysis. In our case, we use 3 steps with data preconditioning, just cleaning it up as much as possible, with the main phase involving cross-correlation within 5 seconds lags. It was a lot of traces, approximately 8,900 trace pairs, and in the end we have some fine-tuning of the results. Which brings us finally to our retrieved data after cross-correlation, where we just examine one example of cross-correlation pairs sorted by virtual source offset. We can look here at both causal and acausal part of the Green function. If we zoom in a bit more, we can see that both plots here show clear linear events. However, what are these linear events? So we can now take our active source gather, pre-sorted by absolute offset. We get the source gather shown to the right, with the red arrows indicating the P wave direct arrival and the blue arrow indicating the surface wave. If we overlay our active gather on top of both causal and acausal part of the retrieved data, we can see that it matches very well with the active source surface waves, which brings us to the conclusion that they are definitely of surface wave origin. To summarize the entire story, both 2D landstreamer and 3D randomly distributed array of wireless receivers were tested for bedrock and weakness zone imaging, and both results, although done independently, conclude that the zones A and B of highest concentration of contaminants are connected and belong to the same origin. Additionally, more fracture systems are possible, and this should be considered for the remediation purposes. If we look at our randomly distributed array, we can see that relatively good amplitude array response is seen, and the surface waves were retrieved successfully. Judging from all the results, we can say that at this site, the random array has great potential for both active source and ambient noise studies in urban environments. I would like to acknowledge Varberg municipality for their help and patience before and during the survey. Also, Uppsala University team for being a great field crew, and special thanks goes to Hamza from Department of Mining and Engineering at Isfahan University of Technology for his help with ambient noise analysis and fruitful discussions, along with Uppsala University, Tirens, Trafikverket, and Smart Exploration for their support during different study stages. Finally, I would like to thank you for your interest and attention, and for other e-lectures, please visit the EAGE YouTube channel. With this, I close my lecture and leave some of the references mentioned before.